So my name is Konstantin Wilms, and I'm here with Chad. We're at Amazon Web Services. We're both on the specialist architecture team. We get to deal, with R&D or interesting projects from time to time. And this is something that's obviously the industry is, this is coming up pretty often right now. How to build a scalable, immersive media solution and then utilize cloud-based architecture, design patterns, etc. So, the challenge here, at least just to start off with an introduction, and then I'll hand it over to Chad, and then we'll look at the solution for building this type of system, if you will. But just as an introduction here, there are a lot of challenges. So if we looked at, say, like a 360-degree video pipeline, which is what we chose to focus on, because it's the easiest to implement, being it's media streaming, etc. From origination to delivery, there are quite a number of challenges. When we look at moving this type of infrastructure onto AWS, so things like stitching, high availability for live streaming, encoding, 4K, etc., ingress bandwidth as well as potentially egress bandwidth for that 4K, the 4K ABR out, and then the ingest stream at high quality. So these are, quite a few challenges here. How do we construct and set up the architecture, the CDN, etc., and then the end devices to actually play the content out. So we looked at this and we thought, okay, we can build a solution as a reference architecture to sit somewhere in the middle here. We won't look at the origination, we'll look a bit at delivery to basically validate the model end to end. And then how would we do that from media encoding standards that we'd look at, transport standards like Dash, etc., and then best practices. So not so much a lift and shift or re-implementation of something, but more a native cloud-based reference architecture, if you will. So there are a couple options that you can look at today for doing these types of pipelines on AWS. And this is similar for other types of streaming technologies as well. Elemental is one option for a full end-to-end pipeline. There's also Elastic Transcoder to process things like proxies for VOD. There are a lot of options in the AWS marketplace as well, and I'll get into some of those. And then finally, you can also do it yourself and build your own architecture. So we looked at this and we thought, what if we focused on the right-hand side and built something from scratch? And then as a reference, we'd give it to our customers to be able to extend and customize after the fact. So this is a very high-level overview, just in terms of the components that we looked at. Obviously, a live workflow with distribution through CDN from source encoders, and then tied into a VOD or NVOD workflow. So whenever we publish a stream to a live encoder, we want to record it to disk, event off it, put it into archive, and then spin up compute to process it into, say, ABR outputs. So there are two models that this addresses. One is B2C delivery for consumers, and then the other one, if we're actually recording those incoming feeds, this is a pseudo mezzanine format. If the source encoder is at a high enough bit rate for non-perceptual quality loss, we could archive that and then have a workflow that pushes that off to third-party organizations for B2B delivery. So you can see there are a number of bullets here, things that we tried to look at to stress upon and to use as sort of guiding items, if you will, in order to construct this. So 100% open source, design that users can expand it, cloud-native patterns, Optimus service consumption. So not consume every AWS service we can, but only consume a few. So that customers are able to repurpose and utilize it efficiently, and then be able to deploy globally, so across all 16 regions, 42 availability zones, and then through 68 edge locations. So really it comes down to CloudFormation to be able to do this part of the puzzle. So where do we start with this if this is the architecture that we're looking to build? The first thing that we looked at was, let's take a step back, and this is maybe also for the audience, just in terms of building a pipeline for this type of media consumption on AWS. So I'll go into a couple options here. This is a fairly straightforward pipeline, where we have media ingest, live or on demand. We have a need to store that content, maybe in a temporary fashion or in a permanent fashion for later delivery as VOD or mezzanine assets. We need to transform that content. That could be editors working against it. It could also be transform as in compute, other derivatives, ABR, etc. And then we may also need to do, say, editing with workstations in the cloud against the content to do, say, cleanup, stitching, etc. And finally, processing, spinning up the resources to process this at scale in an automated fashion. So on the ingest side, there are a number of options here. And really for high bitrate content, the first thing that comes to mind is AWS Direct Connect. So high-speed fiber connectivity from a data center can be paired with, for example, MPLS or other type of connectivity, allowing you to get your content in a deterministic fashion into the VPC for processing. The similar, with the rest of the options here, such as S3 transfer acceleration, or say AWS Snowball, and this is where you have content that you've recorded on site. You may want to move it into the cloud, but it's not live. So it's VOD or mezzanine assets, and these are two mechanisms you can use: transfer acceleration, or put it on a Snowball device and move it into Amazon. For distribution, or also for ingest, CloudFront is an option. And this is more on the control layer, if you will. So if you have a CMS sitting in front of everything. And then elemental appliances, which you can install on-prem to condition or encode the content before pushing it up into the cloud. So there are also a number of partners that you can see here, such as Teradek is one good example there, Aspera, Signient, etc. On the storage side, a lot of this is fairly self-explanatory. But we chose to pin everything to S3 object storage. So essentially, we have temporary storage on compute. But the real, at least assets, if you will, for playout or distribution are living on S3, can be life cycled into Glacier, etc. But there are also other options such as EFS, so NFS storage that can be attached to all of the instances for processing. There's obviously EBS for local storage. And then there are marketplace options to span hybrid cloud, etc. So there's also this need to transform the content that I talked about. And this would be where if we pull, say, the individual camera feeds into the cloud and we then want to do manual stitching, maybe with Premiere, Nuke, etc. So this is where we'd utilize, obviously, EC2 that's then running maybe Amazon Workspaces as a service based on that, or a solution out of the marketplace, or something like Amazon AppStream. So these are all options to give you a Windows or a desktop-based experience in the cloud. And the benefit there is that you have access to things like GPU or CPU compute resources. You have PC over IP that can be pinned to a thin client or a desktop client with a piece of thin client software running locally, but you're keeping the content in the cloud. So the advantage there is you can edit directly against the content via the workspace, or EC2 or marketplace option, and you don't have to shuffle content back and forth, which is critical for mezzanine assets. And then finally, on the processing side, there's obviously EC2 Spot, which gives you low-cost spare GPU and CPU compute capacity. And we thought this was key because this would enable customers to reduce all of the infrastructure costs on the live side and the VOD side. So as Chad will talk about, it's easy to utilize this type of functionality for VOD because we're simply transforming and re-encoding content. For a live workflow, it gets a little bit more complex, and we designed a few things around this to sort of alleviate those problems, if you will. There are also other options, though. So Amazon Batch or AWS Batch is another option to do batch processing. This is pretty useful for, say, VOD processing, if you will. where you can deploy containers and the orchestration system takes care of everything for you. ECS is another option if you look at direct deployment of containers. And why am I talking about containers? One of the challenges here is that when you deploy code such as, say, FFmpeg, x264, x265, etc., in many cases they have a lot of dependencies. They take a long time to compile, even if you have a decent amount of cores on an instance. So essentially, if you build a container that's able to dynamically determine if it's running on a GPU or CPU instance, and I can deploy it in maybe 15, 20 seconds max, it gives me the ability to implement an SLA and pinned to the speed at which I can process my content. So we sort of looked at that as the model here. Could we use Spot, ECS in combination? But there are two other last options here. The one is we recently acquired ThinkBox Deadline. So this is your scheduling for rendering and compute. And then obviously Elemental Cloud is another option here. So to hand over to Chad, we looked at going back to this architecture here. What if we maximized all of these pieces for EC2 Spot usage? And this is key because you can see from this diagram, besides archival storage and distribution, everything else is compute-based. So really, Spot provides you a good avenue to reduce cost from that perspective.
Thank you, Con. All right, so as Con just mentioned, our whole goal here was to design our architecture to make it as cost-effective as possible without sacrificing scale. And so we chose the EC2 Spot service to handle that. So I'm going to talk a few minutes about what EC2 Spot is. So quickly, just a background. So when you purchase EC2, you have essentially three options for purchasing. You can purchase on demand, which is pay by the hour for compute with no long-term commitments. We have reserved instances where you can prepay for reserved capacity for the foreseeable future. And then we also have the spot market where you can bid for unused capacity. And it's great for time-insensitive and transient workloads or stateless workloads such as the one that we're proposing here. All right, so AWS has a lot of excess capacity, right? We have to have the ability to allow customers to scale up very quickly over large regions. So we have a lot of spare capacity, a lot of growth happening, right? So what are Spot instances? So Spot instances are essentially spare EC2 on-demand capacity with a couple of very simple rules, right? So these rules are that the spot market is a market where the price of the compute changes based on real-time supply and demand. And second, you never pay more than what you have bid, right? So you put a bid in. If your bid meets essentially at least the price point of the marketplace, you'll get an instance that gets spun up. If at any point you are outbid, you get 2 minutes to wrap up your work and continue on. Right, so since Spot instances typically cost 50 to 90% less than on-demand compute, you can approach that a couple of ways. Either you can increase your existing capacity by 2 to 10 times without changing your budget, which is a great thing, access to more capacity without increasing any of your spend. Or you could just say take your existing spend on demand and save 50 to 90% off of it on your existing workload. So completely up to you, or it could be a mixture. Either way, I'm a huge fan of Spot, and I think it's the greatest thing since sliced bread. That's why I have that slide there, but give it a try if you can. So let's understand a little bit about what EC2 capacity is. So I'm going to pick a region here. As an example, I have a box of the Frankfurt region looking at total capacity. Every region has at least 2 different availability zones, often more than 2. Obviously, these are different data centers, which means different availability zones are separate pools of physical CPU capacity, right? So AZ1 is a separate storage server room, AZ2 is a separate server room, et cetera, multiple locations. If I slice those up again across different instance types, so here we have P2, C4s, M4s, I2s, et cetera, these are different instance types that are offered on top of AWS. They each have slightly different characteristics. The Ps, for example, have advanced GPU processors. The C's are tailored for computing, M's are general purpose, R's have high memory to CPU ratios, etc. Anyhow, each of those different instance types are separate pools of capacity. If I then slice it up again, within each of those instance types, we have different sizes. So, for example, you can have an 8x, a 4x, an X, or a large. These, within those single families, are also separate capacities. So a lot of excess capacity, a lot of different sets of capacity, even within a single region. And if I slice it up even further, you also have the ability to launch on either shared infrastructure or dedicated infrastructure. So in the case of dedicated, you can launch a virtual machine that lives on a physical server that is not shared by any other customers. And so this allows you to meet requirements for a certain type of workloads, HIPAA, PHI, for example. Anyhow, point being, every single one of these tiny little boxes are separate pools of capacity, and then those have been exposed as separate EC2 spot markets. So quick recap here, right? So if I chose the C4, for example, 2A, 2B, 2C being 3 different availability zones, each of these families is a separate capacity pool, each instance size is a separate capacity pool, each availability zone is a separate capacity pool. In every single region, the 16 regions that Con mentioned, those are all separate spot markets. So let's take a look. Earlier I mentioned there is the market price for spot instances, and then there is the bid price. Key here being you never pay more what you bid, but the reality is that you really never pay more than what the market is currently demanding. So I can safely put a bid in for, say, 50 cents per hour for a given instance, but if the market price is only 10 cents per hour, you will only pay that 10 cents per hour. And as the market fluctuates up and down, your price then will readjust by the hour depending on where the market is. So let's take a look at this. So I have an example here of, looks like in US East 1D, I have an R3 4 extra large. The current market price is just under 18 cents per hour. If I had bid 25% of the on-demand price, you can see that green line there is showing market price. You can see that I probably would have experienced roughly 4 interruptions over that 1 week period of time if I had bid 25% of the on-demand price. If I had upped my bid price to be 50% of the on-demand price, I would have only experienced 1 interruption that you can see there, and I really wouldn't have paid much more than if I had bid the 25%, except I would have experienced fewer interruptions. And the whole reason for that is that, again, you never pay more than what the current market price is. If I had upped my bid to 75% of the on-demand price, my instance would have experienced 0 interruptions over that week's period of time, and again, I would have paid roughly a little bit more than if I had bid 25% of the on-demand price, again, but with 0 interruptions. And I have a lot of room for flexibility in there. So had the market fluctuated even more than it did in this graph, most likely my instance would not have experienced any interruptions. So a couple best practices I just want to call out. You want to make sure that your application and your architecture is as stateless as possible, right? You want to be fault tolerant. You want to deploy your application across as many different availability zones as possible, and you want to make sure that your application can withstand the ability to fail over across those, for example, in multiple AZs. You want your application to be as loosely coupled as possible, right? These are all key things that come to EC2 best practices. The difference between Spot and traditional on-demand EC2 is that you want to be as flexible as possible with your instance types. So that means if your workload can run on maybe a C4 or an R4, an M4, for example, why not use them? So this will allow you to find not only the best price, but also to have access to the most capacity, because again, every single one of those capacity pools are unique and different, have different price points. If you're in a mode where you're running batch loads, batch workloads, and it really doesn't matter what the underlying processor type is, because you're just pulling jobs from a queue and you're getting the work done and then you're moving on to the next one. Spot is a great use case for that, because if you can be as flexible as possible across your instances, you'll be in the best position possible. Right, so some customers will say, but my instances cannot be interrupted. I have a job that needs to run for a certain amount of time. I like to show this slide. Cloud Health did a study showing that 21% of all instances run less than an hour, 35% run less than 2 hours, 40% run less than 3 hours, and in total, roughly 50% of all instances live less than 6 hours. Right? So for those jobs that just cannot be interrupted, where if you were to lose an instance within that period of time, your job would have to be restarted, and that would be a critical thing for you that you don't want to happen. There is the ability to bid on blocks of time on the spot market, and these are called spot blocks or reserved duration periods. These can be reserved for up to 6 hours of time. Anywhere from 1 to 6 hours, you receive roughly 50% off of the on-demand price in exchange for reserving a spot block, and it's just another parameter that you pass to your API call. So one last slide here. This is an example of running some batch processing with Spot over a 30-day period where we requested 1,000 virtual cores over a 30-day period. Over that given time, you can see there was really not much fluctuation. Minimum number of cores that we achieved were 960. The mode was 1024 and the average was 1012. And the average price per virtual core over that 30-day period over those 1,000 virtual cores was just over 1 cent per hour, and that achieved savings of over 80% over the on-demand price. All right, so I'm going to hand it back to Con here, so thank you.
Thanks. So given that, let's look at the design around this, how we sort of implemented around some of the challenges that Spot presents. So there are actually two areas here, and one is these set of end-to-end media requirements, and then the other one is the design pattern that we implemented, and then I'll finally get to the architecture as well. But we had a number of requirements here. So some of these were things we put down that the solution had to actually implement and be able to support. Some of them are sort of ancillary to this type of a solution that you actually wanted to be able to fit into this mold, where if I need better security, right, if I need different formats for ingest and egress, it should be able to accommodate that with minimal modifications. So we don't want customers to have to rewrite the entire thing. Potentially it only fits a certain very small niche. So some of the things we looked at here were it should support secure compute. So by compute, I mean if we run a cluster, we should be able to remove SSH from it and use something like Systems Manager, which is an AWS service, which allows me to run command line, executions against any of my instances that are running in the cloud without requiring a shell. So that's essential from that perspective for managing a cluster. Content should be secure at rest and in flight, so things like snapshotting instances, being able to utilize HTTPS through CDN, being able to utilize maybe RTMPS for ingest, etc. We should support all of those. And then secondary, obviously live and on demand for the 360 content, we should be able to support both of these models. We chose to use RTMP, but there are other options such as RTP with FEC encoding. We didn't look at that because we felt it may put additional burden on any customer that's initially deploying this, but it's not to say it can't be swapped out. On the ingest side, we chose to look at bitrate conformance. So if you have an encoder, it outputs 4K, you can potentially conform it to a lower bitrate. And it allows you to bring up this solution and not have to have, say, direct connect in place. Maybe a high-speed internet connection is good enough to basically test out the waters, see how it works with 360 content. Part of that conformance could be reducing the frame size to validate that the entire end-to-end chain actually does work. And this is where Spot is obviously key because we still pay, a fraction of the price that we would if we were spinning up, say, 64 plus cores for high-speed processing. And then we focused on HLS and Dash, being able to support both of those for egress, and then H.264 AAC sort of as a underpinning set of codecs. So obviously we talked about Spot. And then secondary to this, and I talked a little bit about this, were the components that we actually run on this. So since we said 100% open source, we chose Nginx with the RTMP plugin. And it allows us to do things like fan out the workload to additional instances. It allows us to easily containerize it, and then also utilizing FFmpeg in combination with that. It allowed us to test out things like various types of filter transforms, of which there are a bunch of those available on GitHub, for example, the Facebook transform filters. Just to be able to test taking, say, equirectangular transforming to cubic, what that stress would be on, say, an origin server, and then how we would decode that on the client. And on the client side, there are a couple options such as Forge.js, Clapper, Unity as well. On the Unity side, there are a couple of third-party plugins that give you HLS support, for example, and then you can build a scene with, say, spherical projection, if you will, in order to build a client pretty easily. So these are sort of the components that we used and the directives that we used to build this and some of the constraints. And then the architecture patterns, and this is where I was talking earlier about not just a lift and shift of what we might do, say, on-prem for a workflow, but how do we make this native for cloud? So these are a couple of the patterns that we used. So obviously the primary pattern here is to represent all of the infrastructure as code using CloudFormation. So this gives us the ability to then stamp out this stack in all of those different regions and availability zones across the world and do it in an error-free with a repeatable fashion. So there's no operator involvement, apart from, say, configuring some endpoints. We use the event-based pipelines for everything. So any content that lands in, say, S3 generates an event. It goes into a notification queue, and then a cluster is spun up that uses the depth of the queue and the age of the oldest item in the queue as a way to scale up and down that cluster for processing bursts of content arriving. We used some other, fairly common streaming infrastructure patterns, if you will, such as the origin proxy pattern. So in this case, we move what would typically reside on the CDN up to the origin. So we have a fan out to protect our two origin servers that are doing the 4K encodes, for example. And there's failover between those two. We used a fairly simplistic service discovery pattern via using EC2 instance tagging. So this way, whenever an instance comes up, it tags itself with a set of tags that allow other instances in the downstream path to discover who is the primary encoder, who's the failover encoder, and then reconfigure their configuration files as they boot up. So that's fairly essential. So that's one option, is also DNS. However, the tagging-based option allows you to do immediate configuration without having to worry about, say, DNS timeouts, etc. For the actual instances, we use the bootstrap container pattern. So I talked about that. Immutable infrastructure is key here. If you figure out you may be stamping this out in multiple locations, you want to simply destroy the infrastructure when you're complete with it. And this is key for this type of pipeline, because we figured a lot of the customers that could utilize this would want to implement it in such a fashion that they bring the infrastructure up for an event and then tear the infrastructure down when the event is complete. And then, high availability is key. So multi-availability zone, we targeted that as well. So we wouldn't target, say, 2 availability zones. If we had access to 3, 4, or 5, we deploy infrastructure to all of those. That way, from that kind of multi-server pattern, we're fully AZ, fully infrastructure aware, automatically without the customer having to do anything around that. And then the last item, decoupling. So this is an event-based infrastructure. We need to decouple the code, and it's essential because we have these compute resources that are often tapped out. All the cores are active, so we want to be able to span that infrastructure out. And then things like events that come into buckets, we want to be able to put them into, say, a FIFO queue and have those queue items not be lost. So completely asynchronous, completely decoupled infrastructure. So the actual solution, this is sort of a simplistic view of it. So we built a CloudFormation template around this to deploy all of this. And you can see here, this is what would be represented in, say, one region across multiple availability zones. And I'll quickly walk you through the actual operation of this pipeline. So we have a source encoder that publishes, it discovers the primary and the secondary origin, either via primary backup or via DNS failover. It publishes to the primary origin, which then does the initial transcode of the conformed content. Where it goes from there is it actually loops the content back to localhost, which then gets packetized to HLS and dash. So to packetize HLS and dash from incoming bit streams is fairly low CPU overhead, very minimal, because we're just looking at the stream and segmenting it. So we ran both of those on these origin servers, but you could actually fan that out as well. And then you can see downstream from here across multiple availability zones to give us high availability. We have this notion of a spot-based fleet coupled to an application load balancer. So we have one downstream CDN CloudFront, but what if we had many downstream CDNs? What if the event was popular and we maybe had 100,000 viewers, etc.? There's always this notion of origin offload at CDNs, but that still means that maybe 10% of the traffic comes through to origin. So for a very popular event, that could equate to maybe hundreds of megabits of traffic hitting our origin fleet. So in order to alleviate that load, we built this edge fleet, which sits as almost a proxy sandwich, if you will, between the backup and primary origins and the downstream CloudFront or CDN destinations. So the key thing there is that how do we do this with Spot, right? These instances could maybe be turned off with 2-minute notification. So what we do on these edge fleet nodes is when they spin up in an order scaling group that's driven by the amount of requests and data coming in for requests for data, we basically have them come online and then monitor their instance metadata to see if they've received a termination request. If they have a termination request, we know that we're feeding HTTP data through this chain. So it's very quick for us to drain stop the instance and shut it down and detach ourselves from the load balancer. So that's basically how we handle this. We proactively monitor to see if Spot is going to send us termination. We drain stop ourselves on the instance and we detach ourselves from the application load balancer. So that enables us through this decoupled fashion to cope with any problems or challenges or timeouts, etc., terminations that we may get through Spot in a very simplistic way, if you will. Secondary to this, when the source encoder is publishing, we generate an event and we record to local EBS disk, which could be provisioned IOPS, so high-speed SSD. When the encoder stops, we mark the end of that, which is actually built into the Nginx RTMP stack. And from there, we move it into an ingest bucket. And when it lands in the ingest bucket, we generate an event, which is built into S3 as one of the service options. And those events go into a queue. And like I said, we can use the depth of the queue, the age of the oldest item, to determine if we have a constant velocity that we need to scale up, or we just have a limited burst for this set of time, which maybe we need to scale up just one instance instead of 10. And we basically process that using Spot once again, put the HLS and dash derivatives for NVOD into an egress bucket, and then the CDN is able to access that directly. So there are a couple other things. Some of these I talked about just as ways to expand the system that we looked at. It should be able to support these: batch encoding, containerized encoding, archive of mezzanine assets, maybe to Glacier. Maybe there's a full OTT CMS or DRM attached to this as well. And then we've put this reference architecture together. We'll have it available soon, and our goal is to make it available to all customers. You can feel free to ask us about it. We'll get you the info and so forth. But thanks.